you a function, and I'm just going to ask you, like, go like you were going on your homework on Friday, solve it. We're just going to kind of clear up some directions about, like, what does it mean? What should your answer look like? Those types of things. And then we'll talk about the Descartes rule sign and the lower and upper bound test. So what I want you to do right now, I got this polynomial here on the board, f of x. I'd like you to write it down in your notebook. I'd like you to do all the solving. Okay. And if you want to work with your small groups, certainly, okay, work with each other. That's totally fine that you're having discussions. In the end, you want to make sure you've done the two things that the directions say, which is to write f of x as a product of linear factors. So maybe have a discussion about what that would look like, and then make sure that you've also listed all the zeros. So I'm just going to give you some time to work on that. Probably about 3 or 4 minutes is all you need for this one. Okay, so I'm hearing from the crowd possibly a -2. You should have started with that rational zero test, looking at factors of your constant, factors of your leading coefficient. Notice that when I take 1 over 2 and I put them over 2, I only get one new zero for that list, the plus or minus 1/2, because 2 over 2 would be 1, which is already on the list, so you don't need to write it again. But someone said -2 works, so I'd run through that. Oh, yep, I'm getting the same thing. So in terms of my zeros, we could say -2 is the solution. Where did you go next if you found that -2? Mason?
Okay, so I did that thing with cubics, where if it's like you can factor the first two and the second two and do that thingy.
Yeah, that's an option that you have here. And if you look at the bottom of your synthetic, I want to try to left right there. Okay. If you look at the bottom of your synthetic, you can sometimes tell, based on the numbers that are down there that are going to be the coefficients to your cubic, if it's going to factor by grouping. That's what that's called. Since it goes 2, 1, 2, 1, it definitely is going to factor by grouping. So that's an option for you, and I will show you the factor by grouping here just because that's a helpful tool we can use. Oops, plus 1x squared, sorry, if I write it correctly. Plus 2x plus 1. And so that's that one where we say, okay, put the first two terms and the last two terms together. What can you take out of 2x cubed plus x squared? X squared. You're left with 2x plus 1. What can you take out of 2x plus 1? Not a lot, so you always take out a positive 1. So you put a plus 1 behind it, and you're left with 2x plus 1. Now, the factor by grouping method only works if those two parentheses that you get are exactly the same. Okay, so since they're both 2x plus 1, I can say that that is one of my factors, 2x plus 1, and my other factor is made up of the coefficients, the x squared plus 1. We've talked about this before. It's like you're undistributing or factoring out the 2x plus 1 from both of the terms. Okay? And so if you use Mason's method, which is to factor, then at the end you can set your factors equal to 0, correct? So this is a surefire way to find my other solutions. I would set 2x plus 1 equal to 0 and set x squared plus 1 equal to 0. This is going to give me a -1/2, which I can add to my list. And this gives me what for solutions? X squared equals -1. Plus and minus I. So plus or minus I. So I have all 4 zeros now. They're all listed up at the top there. Did anybody find those zeros differently besides Mason's method of factor by grouping? If you didn't, can you see how else you might have gotten the same solutions? What would be your other option? Danny? Yeah, I mean, you really can continue with guess and check. We might say, like, maybe that's not the most efficient method if we can absolutely factor by grouping, correct? So you could have gone back up here and just built your synthetic off of what was already done, and eventually you would have tested negative 1/2, and that would also work. And then at the end here, this would be 2x squared plus 2 equals 0. When you solve that, you're still going to get your plus or minus I. Okay? So that would be a solution. The other part of the directions on here asks you to write out the linear factors. So what does that mean? Did anybody get to that part? Have a quick conversation with your small groups. What's it going to look like when you write out the linear factors? Conversation just real quick. Haley, what do those linear factors look like?
X plus 2, X plus 1/2, and X plus or minus I.
Plus or minus I, I'll write them out separately. So, like if I'm looking at positive I, it would be minus I and then X plus I. So they each get their own. But yeah, it is plus or minus I. But this way, if you FOILed it, distributed them, you'd get all of them. Okay, so yeah, that's pretty much what we want for linear. There's one factor I'm going to change. Mason?
You can write x plus 1 plus 2x plus 1.
Yes. Because think about how often in factoring, like when you factor things by either your method where you do that swoop thing, or if you're just doing factor guess and check, I don't know what that thing is called. Rainbow method. Okay, if you're using the rainbow method or you're just factoring by guess and check, think about how often one of your factors looks like x plus 1/2. Really never, right? You don't think about factors as being 1/2. So anytime you have one that has a fraction like that, whatever the denominator is, that's really the coefficient to x. Okay, so I would prefer, and I want to see, you write out your linear factors. You're going to change that to be 2x plus 1. And then you still have x minus I and x plus I. Okay. Think about 2x plus 1. If you set that equal to 0, you would subtract 1 and you divide by 2. It would still give you negative 1/2 as your solution. Okay, but that looks more like what you get in an answer to a factor. Good. Excellent. You guys did a great job of solving. And we have the two methods of synthetic guess and check and then factor of the cubic. So we want to move along and talk about Descartes' rule of signs. So this should sound familiar. Jot these things down. But you should have seen Descartes' rule of signs before.
That's Descartes.
Yeah, I don't know, his name, you say Descartes. But then I didn't know if I should put the extra apostrophe S.
It would just be there's no S.
But then you would still say Descartes.
Yeah.
That confused me.
But should we use this name? Do you know that language?
It's French, so you wouldn't use it.
Oh, they do. Oh, yeah.
I don't know if you would.
I don't know. What is Descartes? But you don't say Descartes.
Yeah, I would just say Descartes. If you're an English speaker.
I know we must pull up.
We would just say Descartes. And
It's spelled like this and you're pre-calculus. So, the rule of law. Let f of x be a polynomial with real coefficients and a constant term not equal to 0. If your constant term is 0, that means all your other terms have some amount of x's in them, and you can factor that x out first, and then begin Descartes with the new polynomial. Okay, so if that ever happens, just factor out the x, or x squared, whatever that may be. For positive zeros, you're going to look at the original function f of x, and you're going to count the number of variations in the signs from term to term. Okay, so you look from the first term to the second term, sign change, yes or no. Second term to the third term, sign change, yes or no. whatever number you count for the number of sign changes in the original polynomial, the number of positive zeros will be equal to that number or less than that number by an even number, and I say less than that number by 2. And if you could subtract 2 again, do that. So let's say you have a long polynomial and you have 4 sign changes. Either have 4 positive real zeros, or 2 positive real zeros, or 0 positive real zeros. If you count your sign changes and you have 3 sign changes, then you have 3 or 1 positive real zero. The best one, in my opinion, is when you get 1, because then you know you have 1. Or when you get one of the odd ones, 3 or 1, because you absolutely know it exists. The even ones, it could be 0, so that's always kind of iffy. Now the rule is almost identical for negative zeros, but you got to pay attention to that you're not looking at the original function, you're now looking at f of negative x. So you can go back to the original function, you're going to replace all the x's with the negative x, and whatever that simplifies to, you're going to look for sign changes there. But then the rule is the same. You'll see in my example, I use a shortcut for f of negative x. Since we're working with polynomials, if we raise negative x to an even number, then there will be no change of sign in the f of negative x. If I raise negative x to an odd number, then in the f of negative x, that term will change in sign. So we can use that as a shortcut. Same rule, just got to look at f of negative x instead. Okay, so we'll look at one quick example where we just count the number of possible zeros, and then we'll talk about upper and lower bound tests. Do you see my cursor? Never know where it is. So we want to describe the possible real zeros. And this is fair game for a question on a problem set, on a quiz, on a test. I could ask you just simply to use Descartes for this. So you need to know Descartes. I could ask a question related only to Descartes. Okay, first we're going to check for positive zeros. And when we check for the positive zeros, we're going to start with the original function f of x. And we're going to start at the very beginning, that's x to the 4th, which is positive. From x to the 4th to x cubed, is there a sign change? No. X cubed to plus 3x squared? No. 3x squared to negative 1? Sign change. So we have 1 positive real zero. Absolutely. Because I can't go less than that by an even number and still be reasonable in terms of I can't have negative 1 positive zeros, then that's the only solution, or possible number of solutions. For negatives, I need to create f of negative x. Okay. So we have some experience with this from our even odd test for symmetry. So when I put negative x into the first term, I'm going to raise it to the 4th, which makes it positive, so it's not going to change signs. It will remain x to the 4th. When I put negative x into this negative x cubed term, that will become negative, changing the sign of that term, so this is now negative. Plus 3x squared, negative x squared is going to be just positive x squared. When I multiply it by plus 3, it will still be plus 3x squared, so no sign change. And then this one won't have a sign change because it has no x. Okay, so the only term that changed signs was the one with an odd exponent, x cubed. And now I go through counting up sign changes. From x to the 4th to minus x cubed, do you have sign change? 1, 2, 3. So that's telling me for my possible number of negative zeros, I either have 3 or 1. So I definitely have at least one real positive zero, and I have one real negative zero. Okay. Now, it's possible that all of my zeros are real if I have 3 negatives and 1 positive. But it's possible, like, if I have 1 and 1, then my other 2 are imaginary zeros. Okay. Now, lower and upper bound tests. These you have not seen before. Did only John see me too? No, you saw that?
Yeah,
Did you see the look at pyramids?
yeah, I was afraid to, like, because if we were gonna fall, it would be towards
It
me.
would, I could possibly damage your face.
Or, like, I don't know, I would just feel bad because they'd be like, did you see that? And I'd be like, yep, it was my desk. And then
It
I'd
would,
feel
it would
bad.
heavily damage the psyche of Jennifer.
Yeah.
Affect her for years to come, ruin her educational environment.
Yeah, she'll be scared math class forever.
I would even sit in the front seat, like, I'd be like, no. Freak out every time I go.
I have never fallen on a student before.
Yet.
There's always a first.
There's a nice buffer right here. Sometimes you're way closer to me.
I know,
You should
but
feel
then, like,
glad that Mrs. Baker has this spaced out so nicely.
I walked into the sixes once.
It's a fear of mine, which is why I just about had a heart attack.
Like sitting, I didn't like laying in the aisle or like just down, face plant.
That's my greatest fear.
It's okay, I'm tough with you. I'm dumb, like,
Okay, let f of x be a polynomial with real coefficients and a positive leading coefficient here. So this test only works if we have positive leading coefficients. You're going to do everything normal. So you're going to create your possible rational zeros using the rational zero test. You're going to check them with synthetic guess and check. And that's really what this line is saying. Divide f of x by x minus c using synthetic division. That's normal. That's nothing new to you. Okay. If the c that you choose, so the zero from the possible rational zeros, if that is a positive zero that you're checking, and the following happens, then you can find an upper bound. And the following is, if c is greater than 0 and each number in the last row is positive or 0. So if in that bottom row of synthetic you have no negatives show up after division, whether it's a 0 or not, then that tells you that's an upper bound. By calling it an upper bound, it's saying in that list of possible rational zeros, don't check anything higher than this number because it's now the upper bound. There is a check for a lower bound. It's a little bit different because you're not just going to be looking for negatives or zeros. You're going to be looking at that very last line of synthetic. And what you want to see in that last line of synthetic is alternating signs. So the numbers at the bottom of the synthetic are positive, negative, positive, negative, positive, negative. And 0 would count as a alternating sign. If that's the case, when you divide by a negative number, then you're calling that number a lower bound, and you would not choose to check any of the numbers that are less than that because they won't work. So this is, again, just a tool to help you work smarter, not harder. This is a test I won't specifically ask you about. So, like, I could give you a question just about Descartes and say, tell me the number of possible zeros that are positive and negative. And you would have to be able to answer that. This, I won't test you over specifically. It's just something you could use if you were going without a calculator. And so it helps you kind of eliminate some choices. The last slide that we're going to look at today is an example, and I'm going to go through the example. I'm going to tell you about my thought process, how I use Descartes and lower and upper bound tests. to make my work go more smooth. Okay. So the example that we're going to look at, so kindly pointed out to me by a student in first hour after I didn't, we could factor by grouping.
Okay.
Oh, yeah.
True. But we're not going to because I want you to see my thought process. But that was a really good point, and you could always look for that in cubics. And beyond, I suppose, if it had only 4 terms. Okay, so if I was starting this problem and it just said find the real zeros, I would, of course, start with my rational zero test, finding my P over Q list. So I look for factors of my constant, 1 and 3, and then I look at factors of my leading coefficient, 1, 2, 4, and 8. And I make this list of possible rational zeros. And I take 1 and 3 and I put them over 1. Then I take 1 and 3 and I put them over 2. Over 4. And over 8. And I have created quite a nice list. 8 positive and 8 negative possible zeros. So that list is kind of longer than usual, and I'm thinking I don't really want to have to check all of those. Okay. If I don't want to check all of those, I could at least check Descartes. I use Descartes' rule of signs. And first I'm going to start by seeing how many possible positive zeros do I have. So I look at the original function and I count the sign changes. I've got 1, 2, 3 sign changes. So I have 3 or 1 positive real zero. Okay. For the negative part of Descartes, I want to check f of negative x. And remember, I would just plug negative x in. If I plug it in and it gets raised to an odd, then that term changes sign. So 8x cubed has an odd exponent. It's going to change signs and become negative. So this will be negative 8x cubed. The even exponents will keep their signs, so minus 4x squared. Plus 6x will change signs. Negative 3 has no x, so it won't change signs. And what I notice in f of negative x is there is no variation in sign. All the terms are negative. So that means I have 0 negative real zeros. And that just tells me don't check negatives. When I do synthetic, where I would normally do positive 1, negative 1, positive 3, negative 3, I won't check any of the negative numbers because Descartes tells me there are no negative real zeros. So don't waste your time. Okay. I can't do upper and lower bound tests until I do synthetic. So those are kind of an afterthought after you start going with synthetic. I'm going to drop in the coefficients to the original polynomial. And I'm just going to check like I normally would. I would start at 1. Okay, 1, 3, 1/2. I'd go down the list because I like to be ordered. And when I do 1, I think you can see it's not going to work, right? But if I finish it out and just look at all those numbers at the bottom of synthetic, you notice all of those numbers are positives, right? Because all of these numbers at the bottom of synthetic are positive, 1 is an upper bound, meaning no zero from this list that is greater than 1 will work. I've just identified 1 as an upper bound. So where I would normally do 1, 3, 1/2, now I'm going to go 1, 1/2. There's no point to checking 3 because I have an upper bound right there. Are we okay with that idea? Okay. And I believe 1/2 works. 8, negative 4, 6, negative 3. Put my 1/2 here. Yeah, that works. And I would have been able to get that by factor by grouping. If I wanted to find the remaining zeros, this used to be cubic, so now I have a quadratic. 8x squared plus 6 equals 0. When I start solving that, subtract 6 and divide by 8, I'm going to get negative 3/4. And if you look at the directions say find all the real zeros. What do you know about this solution? It's going to be imaginary. So if the directions really did say just find the real zeros, you could stop. We could keep going if we wanted to and take the square root of both sides. When you square root this negative 3/4, you should think about it like the square root of negative 3 over the square root of 4. Then you can simplify the top with I. Get plus or minus I square root of 3, and then on the bottom the square root of 4 will be 2. If the denominator on that one didn't come out nicely, like the square root of 4 does, then you could go back and rationalize your denominators if you needed to find all the zeros. Okay, but we don't have to here, so we really won't worry that much about it. But in terms of finding the real zeros, we found the real zeros. Okay. These are my other zeros that are not real, and then I have 3 total. Does that make sense how I use Descartes and lower and upper bound? Okay. You really, like, in order to use the lower and upper bound, you really have to be thinking about them as you run through synthetic guess and check. Hitch.
How do you gain the 1 on the positive card?
Oh, because when I counted up the sign changes, there were 3 of them, right? Up here. 1, 2, 3. So the rule says the number of positive real zeros is equal to that number of variations in signs, which is 3, or less than that by an even number. And if you think less than that by an even number, you're really thinking if you could subtract 2. So 3 minus 2 gives me 1. If you had 5 sign changes, it would be 5, 3, 1. So you always just subtract 2 as many times as you can. Good question. Anything else? Okay, you have an assignment from your gold sheet.